In this chapter we are dealing with three-dimensional shapes, so we need to start off with some vocabulary related to three-dimensional shapes. First is a polyhedron. Now we won't be dealing with polyhedrons, but it is here to set up the definition for a prism, which we will be using. Officially, a polyhedron is a three-dimensional figure whose surfaces are polygons. All of these shapes here are polyhedrons. Like I said though, we only need polyhedron for the definition of a prism, which is just a specific type of polyhedron. We won't actually be dealing with any of the shapes on this page. This is the definition of a prism. It is ugly. It is a specific type of polyhedron. All I can say when I see this definition is ugh, since it is so dense. This is not helpful for most of you for understanding what they are. So let me walk you through what needs to be true in order for a polyhedron to count as a prism. To do that, let's start off by having pictures of the two of them. Now let's get rid of this horrid definition so I can focus in on a couple of things. In order for a polyhedron to be a prism, we need to start with two congruent and parallel sides. Not all polyhedrons fit that description, but this one on the left does. Both of these shapes have multiple pairs of congruent and parallel sides, but let's focus in on these ones here, which would be the top and bottom of both shapes with how they are currently oriented. And yes, I know we can't really see the bottom of the one on the left. Use that wonderful imagination of yours. These congruent parallel sides are our starting point. Now so far I haven't shown you any difference yet. Now it's time for that. You can imagine that the two congruent parallel sides have corresponding vertices. Since they are congruent, a vertex on the top will have a matching partner on the bottom. Here I have shown you a pair of corresponding vertices on both shapes. Now we get to the difference between these two shapes. In a prism, the corresponding vertices of the two congruent parallel sides are connected by a straight line segment. On the left shape, these corresponding vertices are not connected by a line segment. The shape bows out. That's why it isn't a prism. On the right shape, the corresponding vertices are connected by a line segment. Those are the two properties that a polyhedron needs to have before you can call it a prism. On this page are a bunch of examples of different types of prisms. Notice all of them have two congruent and parallel sides, which are connected by straight sides. Now when I want to name these prisms, I need to look at those two congruent parallel sides. For the purple one on the left, the two congruent parallel sides are squares. Since those polygons are squares, I would say that the purple prism is a square prism. For the light blue one next to it, the top and bottom are pentagons. Because they are pentagons, I would say that it is a pentagonal prism. Using the same logic, I would say the top right one is a hexagonal prism, and the green one is a rectangular prism. That is how you name a prism. Now that we have established what a prism is, and how you name it, it's time to do some prism anatomy. First we have faces. The faces are all sides of the prism. These are all of the faces of this prism. For a hexagonal prism like this one, there are 8 faces total. These faces are split into two categories, bases and lateral faces. The two congruent parallel sides are the bases. Here the bases are on the top and bottom of the prism. But like the other bases we have done this year, the base does not have to be down. A prism certainly could be lazy, taking a nap, and lying down on its back, where the bases were not on the top and bottom of the page or screen. If those two sides are the bases, then the other faces must be lateral faces. All of the other faces are lateral faces. So for this hexagonal prism, there are 8 faces total, 2 of them bases, and 6 of them lateral faces. The red ones are the bases, and the blue ones are the lateral faces. And yes, I know the bottom one looks purple and not red since it is being viewed through a blue piece, but it really is a red side in truth. Now we come to the edges. You can probably guess what the edges of a prism are. They are the black line segments. They are where two faces intersect. Just like the faces, we can classify edges in 2 ways. Some of these edges are base edges. Some of these edges are lateral edges. The base edges are going to be really surprising. They are the edges of the base. I have highlighted them in red here. If those are the base edges, then by the process of elimination you should be able to figure out which ones will be the lateral edges. But officially the lateral edges are the edges in between two lateral faces. I have once again highlighted them in red here. Vertex you can probably guess without me telling you. Officially, a vertex is a point where 3 or more faces or edges meet. I have highlighted 5 of the 12 vertices of this prism. We have done many altitudes for different shapes, and they work exactly the same here. An altitude is a perpendicular line segment that connects the bases. Every altitude we have done so far has been perpendicular to the opposite side. They always tell you how high something is. Here it tells us how high the prism is. This is splitting hairs, and we have done the same thing before, but the altitude is the actual line segment, and the height is the length of that altitude. Nothing much to say here. When you hear the term right prism, the right part should bring to mind right angles. Officially, a right prism has rectangles for lateral faces, and the lateral edges are also altitudes. So these are all altitudes, and that means that these are all right angles. The net effect of all this is that the right prism stands straight up. Unlike right prisms, which are straight up and down, Oblique prisms are slanted off to the side like this one here. In an oblique prism, some or all of the lateral faces are non-rectangular. The altitude for this guy would be something like this here. That's about all I'm going to say about oblique prisms though, as they are not very common and not usual at all. You don't see many buildings built slanted like that. You just don't come across them much. Right prisms are far more practical and common. In fact, this is one of the few things that you can assume in this class. If we tell you something is an octagonal prism, for example, you can assume it is a right prism. Now we get to cylinders like the purple one here. A cylinder is not technically a prism since it doesn't have polygon bases. But for all intents and purposes, a cylinder is exactly like a prism, except it has circles instead of polygons for bases. The altitudes and heights are the same. There are right cylinders like this one that stand straight up and down. There are oblique cylinders, which I won't bother drawing, which are slanted off to the side. Other than circles instead of polygons for bases, there is only one other cylinder-specific thing to note. A cylinder has a radius. The radius of a cylinder is defined as the radius of one of the bases. That isn't too hard to remember, I bet. That's the only really new thing about a cylinder compared to a prism. Now we get to the areas. The lateral area of a prism is the sum of the areas of the lateral faces. So you could technically brute force it without a formula. You would just individually find the areas for all of these lateral faces and add them up. With lateral area, we mean the area of the whole shape except you leave the bases out. That is the lateral area of a prism. For a cylinder, the lateral area is also the area of the whole shape except you leave the bases out. You can visualize it with this cylinder, but I bet you have seen a cylinder where you are missing the bases. How about an empty toilet paper roll? That's a cylinder you have likely seen that has no bases. The lateral area for this roll is simply the cardboard it took to make it. In fact, if you want to visualize it even better, you can cut the tube and unroll it. The lateral area is actually just the area of this rectangle on the right. Fear my amazing crafting skills. A moment of silence for my toilet paper roll that gave its life to help complete this video. Surface area is different because the surface area of a prism or cylinder is the area of all sides of the shape, bases included. Since both a prism and a cylinder have two bases, the surface area is the lateral area plus the sum of the areas of two bases. Surface area is sometimes called total area. We have finally gotten to the formulas. First, we will do the lateral area formulas. For the lateral area of a prism, the formula is pH. P stands for the perimeter of the base. Remember that there are many different types of prisms. Their bases can be a lot of different things. So you find the perimeter of whatever shape the base is and plug that into the formula. That's for a prism. Remember that I said that cylinders behave nearly identically to prisms. Well, they are so similar, in fact, that it actually uses the same formula. However, there's one thing you need to be aware of. You have a choice to make. As I just said a bit ago, the P stands for the perimeter of the base. For prisms, that can be a lot of things. So we can't be more specific. However, for a cylinder, I do know what the base is. The base is a circle. So I can put in something more specific for the P. What is the perimeter of a circle? It's the circumference. So I can put the circumference formula in for P and end up with 2 pi RH. Here's the choice you have to make. Your first option is you don't memorize a new formula and you just use LA equals pH. That is perfectly fine. If you choose this option, you will constantly have to ask yourself what the perimeter of a circle is, decide it is circumference, and then plug it in for P. It isn't hard, but it is an extra step. Your second option is to memorize the cylinder-specific lateral area formula, LA equals 2 pi RH. If you go this way, you have to memorize a new formula, but it will save you a step when solving. The choice is yours. Do you want to memorize something extra to save a step when solving? About half my students generally pick each option. There is no wrong way to go about it. Do whichever you think will make you most successful. Now we get to surface area. When I introduced surface area, I said it was the area of all sides, the lateral area, and both bases. That is literally the formula. To find the surface area, you first take the lateral area, and then you add in 2b. What does capital B stand for? It stands for the area of one base. A prism has two bases, so we are adding in 2b. A prism has two bases, so we are adding in 2b, the area of two bases. Once again, the formula that we have is pretty generic. Area of one base isn't very specific. But remember that prisms can have a lot of different bases. You need to find the area for whatever base you have. Some bases, like squares, are easy. Some bases, like the regular polygons, might take some work. Basically, any of the area formulas that showed up last chapter might be used here depending on what your base is. Sound fun? Yes, you actually have to remember all those formulas from last chapter. That's the surface area of a prism. Take the lateral area calculation and add in the missing pieces, the areas of both bases. For cylinders, it is going to be very similar to the lateral area formula discussion. The prism formula absolutely works for cylinders too. You can definitely use that if you like. But for cylinders, we can get more specific. We don't have to use the generic capital B. We know that the base of a cylinder is a circle. What's the area of a circle? It's pi r squared. So we can substitute that in for B to get a cylinder-specific surface area formula. You're faced with the same decision. Do you want to skip memorizing a new formula, but have an extra step when solving, namely replacing B with pi r squared every single time? Or do you want to go ahead and memorize the cylinder-specific formula and save yourself a step? The choice is yours.